Okay, are you able to see that? Anna, does that work for you?
Yes.
Okay. Now I want you to say yes twice. Once is that you can see it, and second, that's the answer you got.
Yes.
By the way, one tip off, and I double underline it or triple underline it, is it should get hydroxide as a product. Now, where you stick the hydrogen on the original base doesn't matter. You know, I stuck it with the NH2 and I made it NH3. If you stuck it with the other hydrogen, it doesn't matter. As long as you stick a hydrogen somewhere, you've got the right formula. Okay, we're now going to look at a problem, a mathematical problem involved with case of B. Oh, wait a minute. Some people didn't see this yet. Let me go back. So if you can't see it on the screen, let me hold the sheet up there for you. Okay, again, notice if you did it correctly, you should get hydroxide as one of the products, and it grabs a hydrogen from water. It doesn't matter too much where you put the hydrogen. Anywhere if they put it here would be fine. So that would be the case of B reaction. Okay, I want to look at a mathematical. Okay, so here's how the problem goes. The problem is, can you actually solve for the value of the constant, case of B constant, given the starting concentration of the base, that's the 0.135 molar, and the pH was measured. Okay, so the first thing you have to be able to do is to write the reaction. Okay, so you take the base, you put it in water, you do a Bronsted reaction, so you get HB and hydroxide. Okay, starting concentration of the base is given, that's the 0.135 molar, plenty of water, and the two products are not given yet. Notice that's also the completion step, because the case of B always means you have a weak acid. It always favors going to the left. Now you have a change step. So you can't have zeros, so everything's going to go a little bit to the right. You're going to lose X of B and water. You're going to gain HB and hydroxide. Okay, at equilibrium, then you have 0.135 minus X, water, X, and X. Notice I circled the X on the hydroxide because that's our goal. If you can find out the concentration of hydroxide, you can convert it to pH. So look at the bottom. So I plugged into the equilibrium constant expression. Okay, now notice you have to know X to solve for K. So if you can figure out the pH, if you figure out the hydroxide ion concentration POH, then you know X. So pH is 11.23. Subtracted from 14, you have a POH of 2.77. So the hydroxide concentration is 10 to the minus POH, and you get an answer of 0.0017. Plug that into the K expression, do the math, you get an equilibrium constant of 2.25. I'm sorry, 2.2 times 10 to the minus 5.
Do you mind, how did you get 2.77 again?
Notice the pH is 11.23, subtracted from 14, and you get the POH. Remember, pH plus POH equals 14.
Oh, okay, yeah.
So if you know,
sorry.
So if you know one, subtracted from 14, you know the other. Okay. Good question. That's the kind of thing I want people to ask, yes. Anything else unclear on it? Okay, for those that can't see that, I'm going to hold the problem up then. Probably the best thing to do if I'm just holding up is take a picture of it if you couldn't do it the other way. Carolyn, okay to go on? Carolyn, are you sleeping?
It's so hard to
Can't
mute.
tell.
Yeah, I'm good.
Okay, should I go on then? Is that okay?
Uh-huh.
Okay. Okay, here comes the next slide. Okay, if things are going well, you should see a solution with a probe of a pH meter in it and a container of hydrochloric acid and sodium hydroxide. Now I'm going to make a very strange statement. If you can control pH, you can control the world. Now obviously that's an overstatement, so I'll kind of modify it. If you can control pH, you can control the chemical world. pH is that important. Now, if this was in the classroom, here's the demonstration I would do. I would ask somebody to name a particular pH they would want. Then I would add drops of hydrochloric acid and sodium hydroxide back and forth until I got the pH you wanted to. The point I'm trying to make is it's pretty easy to adjust pH to what you want it to be. And if you can't see that picture, I'll hold it up so you can see it. Okay, visible okay? Okay, we're now going to do some problems in which we're going to control the pH. Okay, so let me take you through this particular problem. Okay, the chemical reaction is between, or the equilibrium system is between H2S, hydrogen, and HS minus. Now H2S is actually a poison, and its conjugate base HS is actually safe. And I gave you the case of A for it. Now, question number one goes like this. If you adjust the pH to 2.92, what is the ratio of the safe form to the poison form? H2S to HS to H2S. By the way, in Chem 1B, we actually used to use this chemical in the laboratory. And the pH was adjusted to 2.92, and I always wondered if it was safe or not. So that's the purpose of this problem. Now, what makes this problem not too hard is we can assume that we're looking for the equilibrium concentration of these two. So we don't have to go through a start step, completion step, and all that jazz. We can go right to the completion step. Okay, so look at the third line where it says K sub A is 1.2 times 10 to the minus 7. Notice I've written the mass action expression, and I've circled in green what we're looking for. We're looking for the ratio of HS to H2S. Now, what you do is you convert pH to hydrogen ion concentration. So hydrogen concentration is 10 to the minus pH. So 10 to the minus 2.92 is 1.2 times 10 to the minus 3. Okay, so now you solve for the ratio of HS to H2S, which is going to be equal to the K sub A divided by the concentration, hydrogen ion concentration. Notice it turns out they're pretty nice. It's 1 times 10 to minus 4. I rearranged this to make it easier to look at. I made it 1 times 10 to the 4 with the 4 in the bottom, which is 1 to 10,000. Notice that means this is not a safe pH to use this because you have one safe molecule to 10,000 poison molecules. And by the way, we always used to get a headache when we do this from the laboratory. We don't do it anymore, but people used to get a headache, and it makes sense because you have more of the poison than the safe chemical. So notice by controlling the pH, we've actually determined what the ratio will be. Okay, if you couldn't see that, let me now hold
Professor,
it
I
up.
have a question
You
real
bet.
quick. Why is it that we skipped the start and completion step and everything? I missed that.
Right, because we're actually asked for the equilibrium ratio.
Oh, okay.
Isn't that kind of cool? That's what makes these problems kind of nice. So we're looking for the equilibrium ratio, and you don't even care what the start was. You just want to know and remember, pH really represents the equilibrium hydrogen concentration. So we know the concentration of the hydrogen equilibrium, and we're trying to find the other two at equilibrium. That's what's kind of nice about these problems. You don't have to go all through those steps. You go right to equilibrium. Kind of cool, don't you think?
Yeah. Thank
Say
you.
yes. Okay. Okay, so here's the chart. And again, this is kind of hard to have it copied by hand, so I'm hoping if you didn't see the other one, you can take a picture of it. Okay, okay, everybody got that okay? Okay to go on? Anybody still copying? Okay, I'm going to call that H2S problem number 1. And I would now like to look at H2S problem number 2. Same chemical system, different question. Okay, does it show up okay?
Yep, showed up perfectly.
Okay, same chemical system. Now, here's the question. Joe Chemist doesn't want to die, therefore he'd like to adjust the ratio of the safe to the poison to 10 to the third to 1. Let's say 10 to the third is 1,000. So he'd like 1,000 safe molecules for every 1 poison molecule. And the question, what does the pH have to be? Now again, what's really cool about this is we're right at equilibrium. So look at the mass action expression. K sub A, which is 1.2 times 10 to the minus 7, is equal to products of reactants. So the equilibrium concentration of the H2S is going to be 10 to the third, and the HS is a ratio of 1. Okay, so we want to solve for pH. How do you do that? Solve for the hydrogen ion concentration. So look at the bottom line. So I've written the K sub A, 1.2 times 10 minus 7, times 1 divided by 1 times 10 to the third. You can almost do this in your head. You get an answer of 1.2 times 10 to the minus 10. Take minus the log of that, you get a pH of 9.92. So that means if you were to run the system at a pH of 9.92, which you can control, it would be a safe system to have. Okay, and if you can't see that, I will hold up. Any questions before we go on, by the way? Where any of the numbers came from? Abby, seem okay? Luke, anybody there?
Yeah,
It's
here.
okay?
Where it says
Okay.
what's the pH be for HS minus over H2S, is that given?
So ask the question again, please.
Is 1 times 10 to the third over 1 given?
That's exactly right. The given is the ratio that you want. That's exactly right. So the given is the 10 to the third to 1. You want that ratio. What you don't know is the unknown pH.
Okay.
So look at the line where I took the mass action expression. The K sub A equals products or reactants. Okay. Actually, this is kind of cool. Okay. So here's the product over the reactant. Can you see the yellow okay? Okay. So I plug the given in. The unknown is I solve for the hydrogen ion concentration, and therefore I can solve for pH. Any questions on it? Okay, let me hold the chart up then for those that can't see this.